Hi, I'm Jackie Cation. Welcome to NASA's Universe Unplugged live chat, where scientists answer your questions about our videos where the stories are fiction, but the science is real. Today, we're going to talk about the death of stars, as seen in the video Think Tank, When Stars Go Boom. Anyway, you can find the links to our YouTube channel on universeunplugged.org, as well as all sorts of bonus information and downloads for each of our videos. Don't miss any of the episodes by subscribing to us on YouTube and follow us on Facebook to join future live shows. Today, we're joined by Dr. Schuyler van Dyk, who is a scientist at NASA's IPAC Center at Caltech. I'm reading this because it's fancy research. His research focuses on the many types of stars that explode, as well as the evolution of the massive stars that end their lives as supernovae. He also provides support for the closeout of the Spitzer Space Telescope. Welcome to the show, Dr. Schuyler van Dyk.
Good to be here.
All right, we're also joined by Dr. Bill Blair, and he is an astrophysicist and research professor in the Department of Physics and Astronomy at the Johns Hopkins University. His primary research interests involve objects called supernova remnants, which are the expanding gaseous nebulas left over after certain stars come to the end of their evolution and explode as supernovas. He is also currently providing support for NASA's James Webb Space Telescope. Welcome to the program, Dr. Bill Blair.
Thank you very much. Nice to be here with you.
Awesome. Let's start with a clip from When Stars Go Boom before we dive into the questions.
Welcome back to Think Tank. Today's topic is the supernova.
Or when stars go boom.
Sure, why not? Everything set with a thought visualizer?
All systems go.
Let's do a quick check. Think of a planet.
What kind of planet?
Doesn't matter. Okay, fine. Think of something that's not a planet. Perfect. Let's get started. During most of their lives, stars shine by processing fuel. But what happens when they exhaust their fuel after millions of years or longer? A star that is many times more massive than our sun ends its life in a spectacular explosion called a supernova. An explosion so powerful that for a brief period it can generate more light than an entire galaxy containing billions of stars.
Okay. Dr. Van Dyk, what is a supernova and why is it more super than a nova? I know super Skrulls, I know nova core. I don't even know what a nova is. What's a supernova? So if you could sort of unpack that.
So as the video described, supernova is the complete destruction of a star at the end of its life. The star has done its thing and reached the end of its ability to maintain itself, and it ends in an explosion. A nova is much less luminous, much less powerful, and actually survives an explosion. So there's matter that gets dumped onto the surface of a very compact object known as a white dwarf, and that material suddenly explodes on its own, but the white dwarf stays intact. And in fact, there are certain novae that recur over and over. There's just more matter dumps on at a later time, and poof, the matter explodes off, but the white dwarf survives.
Oh, okay. So the supernovae explode and the novae are just before that.
Well, they can be. I might have a chance to describe that later. You got to blame Walter Baade and Fritz Zwicky for inventing this term supernova, because they were just looking at novae that were more powerful, and they called them supernovae.
Oh, well, good for them then. I approve. I'm gonna, Dr. Blair, could you tell us what a supernova remnant is and why? Yeah.
Well, so we pick up the story after the star explodes, and I just highlight the fact that Schuyler already said this, but basically a nova is an explosion but not a complete destruction of the star, whereas typically a supernova destroys the star. Sometimes it leaves behind a stellar remnant, we call it, a thing left behind a pulsar or a neutron star, or possibly even a black hole. But the star as we knew it is completely gone at that point. But that's where it gets interesting to me. The explosion happens, of course, and so the outer layers of the star get thrown off out into space. Initially, for a young supernova remnant, maybe less than 1,000 years after the explosion, we actually can see the star stuff, the ejecta, it's called, from the star that exploded. We learn about the star that exploded from the stuff that it created. And then as supernova remnants, the stuff left over from a supernova remnant, gets a little bit older, that shock wave from the explosion goes out and starts to sweep up interstellar gas and light that up so that we can actually see part of the interstellar gas that is normally dark and we can't see it, but it gets lit up by the passage of this blast wave from the supernova. And so that's partly an older supernova remnant would actually be that. A younger one, we actually see the stuff from the star that exploded.
And so the importance to study this stuff is to find out what stars are made of, and then eventually lighting up that area we can't see. Is that why it's kind of important, or is there other things I'm missing?
Yeah, well, so there's a number of reasons that supernovae and remnants are important. One is the composition. Different masses of stars produce different amounts of various chemical elements. And so if you look at a whole galaxy, you're kind of interested in the ensemble of all the stuff that has come from lots and lots of supernovae over time. Whereas for an individual object, you're really trying to understand the star that exploded, and what that star was, and then what it created to try to validate our models of how all this stuff works and where the chemical elements actually come from.
Because and I saw that in the Universe Unplugged video with Will Wheaton, that's where we get a lot of the minerals, right? From, like, they blow up and then we get copper. I'm not entirely.
Yeah, no, different things come from
periodic table.
Right, exactly. I mean, basically, our understanding of the universe as it started was there was nothing but hydrogen and helium. So all the heavier elements, carbon, oxygen, the iron in our blood, everything was inside a star at one point or another, and it was where it was created from fusion of lighter elements into heavier elements in the stars. And then in supernovae, in the actual explosion itself, there are certain heavy elements that actually come from literally those few seconds as the star is exploding and processing material. You get some of the heaviest elements out of that. Schuyler can probably talk to that better than I can.
Right. Well, I was going to ask Dr. Van Dyk if you want to add to that, and then I also wanted to ask you if we can ever tell from looking at it from a distance when a star is going to go supernova.
Okay. Well, so the only thing I'd add to Bill did a great job of summarizing that. I mean, we would not be here as human beings without supernovae, because they provide many of the chemical elements that we're composed of as life forms. And of course, it's thought that a supernova was responsible for sort of promoting the formation of the solar system at one time, because supernovae are so powerful that they impact energy into the medium of the galaxy, and that energy compresses dense clouds of gas which go on to form new stars. So supernovae are really essential for our existence.
So they move on to create new stars from those gases by compressing. Because we did the last episode was about the creation of new stars. So now I'm sort of putting it together. Thank you.
We tend to kind of talk about the chemical elements that they produce, but of course supernovae pump a lot of energy into interstellar space, where it is able to churn up the gas and dust that is out there already, and that's what starts the star formation process going sometimes.
Right.
And so to get back to that other question, though, Dr. Van Dyk,
your second part, yeah.
Yes.
So
go for it.
So most supernovae come from stars that are in a phase of their evolution called the red supergiant phase. And so a star like Betelgeuse is actually a red supergiant. And so all of the red supergiants in our galaxy will inevitably become supernovae. So if you wanted to tag a star that will potentially explode, your smart money would be on the red supergiants in our galaxy and other galaxies. And the question is, we don't know exactly when. And I also preface it by saying that there is another object that we could talk about, which is even more extreme than supergiants, a star called Eta Carinae, that also is thought to be a candidate for a supernova explosion at some point. But again, if you were a betting person, you'd put your money down on a red supergiant being the next supernova.
And so if you look, sorry for the simplicity, if you look through a telescope and you see a red supergiant, what makes it a red supergiant? I'm just throwing that out there for either of you, actually. I don't know who would.
Oh, well.
Go for it, Dr. Van Dyke.
I'm happy to feel that. So when a star that's more massive than about 8 to 10 times the mass of our sun reaches the end of its evolution, so a star is born, and then a star lives its life by creating elements inside. Bill was talking about this. And so you create ever heavier elements inside that star as it evolves. And of course, the more massive the star, the faster it lives. It's, live fast, die young. And so when the star has reached a point where it's created iron at its core, that's the most stable element to the point where you have to add energy to iron. So iron, you can't get any more energy out of this nuclear fusion process. And at that point, up to that point, the star keeps bloating up to being bigger and bigger and bigger. And so it reaches this so-called supergiant stage. And as it blows up, as it gets bigger and bigger, as it balloons outward, it cools off. So it becomes red in color. So that's the origin of the name. Astronomers aren't very creative. We're not botanists, so we don't use a lot of Latin. We just call them as we see them. So
right.
That's the origin of that term. So a star like Betelgeuse is nearing the end of its life compared to the time when it was born.
Okay, Bill?
I just wanted to highlight something that's probably obvious to everybody, but it's something that's so interesting about astronomy. Somehow astronomers can talk about things like 1 million years and say that's not very long. A supernova, a massive star, lives fast and dies in maybe a few million years.
Wow.
But the amazing thing about a supernova explosion is it literally happens over the course of seconds. So it's the timescales involved in astronomy are really quite astounding, and we tend to talk about things that normally we would think are big times, and those are actually fairly short in astronomy. So 1 million years for a star to evolve and die is a very young star. Most stars, like our sun, is already 5 billion years old and should last another 5 billion years. So, timescales are very, very large in astronomy. So,
I'm knocking on wood about that sun thing. I have this to ask: is I saw on the video, the think tank, which is on universeunplugged.org, that the first supernova that was seen was possibly over 1,000 years ago, and they noticed it because it stayed in the sky for 2 years. Is that something? Is that real?
Yeah. Well, I guess I'll take that one. I mean, there have been a handful of supernovae in our Milky Way galaxy that have been observed by humans, even naked eye. And the Chinese astronomers in particular were particularly adept at recording these things and whatnot. So the Crab Nebula supernova that we'll talk about a little bit later was observed to explode, or when it was first seen at Earth, on July 4th, 1054. And that was recorded in the Chinese records, and it stayed bright enough that you could actually see it during the daytime for a period of time, and then it stayed visible at night for close to 2 years. Yeah,
Wow. And
and that was
that's
long before the telescope. That was
Yeah.
naked
exactly,
eye.
that's the naked eye, right?
Yeah, yeah.
I will say that let's actually look at that animation. So let's take a look at this special animation for a particular supernova that you just mentioned, the Crab Nebula, and you can get that video on Universe Unplugged website, by the way. And Bill, why don't you set it up and then throw to it?
Yeah. Well, so this will be an animation. It starts with some actual pictures, and then it turns into an animation of the Crab Nebula supernova remnant. This is one that exploded about 1,000 years ago, and it's on the one hand, it's almost prototypical of a certain class of supernova remnants, and on the other hand, it's a very strange, bizarre object. But it highlights the fact that supernovae and their remnants emit light over a broad spectrum, from X-rays and even gamma rays, all the way out to radio waves and everything in between. And astronomers like to look at things with different kinds of light because it tells us different things about the object that we're looking at. And for something like the Crab Nebula, what you'll see here is, first of all, a Hubble picture that pretty much highlights the outer nebular structure of the supernova remnant, which is the guts of the star that exploded 1,000 years ago that are being thrown off out into space. But then it transitions over to an infrared picture from the Spitzer Space Telescope that is highlighting the interior gas that is excited from a pulsar that is the stellar remnant of the supernova. Very bizarre object. It's an object the mass of the sun that is only, or a little bit more actually, that's only about 10 or 12 kilometers across. So it's very, very dense. And this massive thing is spinning 30 times a second. And it's the energy from that thing that is energizing the rest of the nebula. And so that's what you'll see in this animation. And I'll try to explain what you're seeing as it goes through. So here's the Hubble picture. The red and yellow filaments here are the star stuff, the parts of the star that are flying off out into space. And then the interior of that, which you see here, is blue, but now you see it as this red light from the Spitzer Space Telescope is actually showing the diffuse gas in the center of the supernova, that is supernova remnant, that is energized by this thing, which is the X-ray image that shows the pulsar in the very center. It has a disk around it from that spinning 30 times a second, and then it actually even has jets of material that go out and energize that red gas that you see there. And so that red gas, if you see it end on here, you can kind of see how that red gas is filling in the center of the object, and the filaments are mostly located around the outside edge. It's almost like a cage of filaments around the outside edge. Now, you can't see all of that in any one wavelength band. You have to look at it with multiple wavelengths, and in this case it's 3 different telescopes in space that have done this. The Hubble telescope is giving you what you see here as the yellow filaments. Again, that's the star stuff that's being thrown off out into space. The red light here is the infrared that's showing you the synchrotron nebula, it's called, the nebula that's excited by the pulsar. And then that blue light is the X-ray emission from the pulsar and the region right around it, including the jets that it is squirting out that are actually exciting that red gas. And that whole red gas and the energy from the pulsar is actually pushing out on those filaments. And most supernova remnants, after it explodes, as it expands, it slows down. But in this case, these filaments are actually being accelerated over time. They're going faster over time because that bubble of high energy gas in the center is pushing out on the filaments there.
Wow. That is
So that's a very complicated object, but it's interesting because almost every supernova remnant is different in some way or another. That's a very bizarre object, but it's a very interesting one because it's close by and we can see it in great detail and actually have been able to follow its development over time now for a number of decades. So it's a special object for us to study.
that is interesting. That you know what I'm gonna do. You can see that whole video, by the way, at universeunplugged.org, and if you missed the beginning of the show, we're chatting about the science in the NASA video Think Tank When Stars Go Boom, which you can see at universeunplugged.org or just click in the link in the comments. But that lends me to this question, and maybe Dr. Van Dyke, is so every star is made out of something else. So every time it goes supernova, it releases it might be its own unique composition. Is that what I'm hearing?
Well, you're kind of on the right track. As Bill mentioned earlier, when the universe first started, it was just hydrogen and helium. But obviously, we're at a state now in our universe where, in the Milky Way and around the solar system, where we have things like iron and gold and molybdenum and all these very exotic elements. And so,
Can you spell
how
that?
did you get? Yeah. For the final on the spelling bee. So how did you get from a state of the universe early on when it was just pure hydrogen and helium to a point where we have all these complex elements? And so it's been this gradual building from generation to generation of stars, where each generation enhances the next generation's content of these heavy elements. And so it will continue on beyond, our existence as stars continue to form. So yeah, you were on the right track.
Okay, and this is a very basic question that I've been. Will our sun become a supernova? Why don't you try that one as well, Dr. Van Dyke?
So the short answer to that is no.
Oh, okay.
So our sun is defined as exactly one solar mass, and so all stars that are on the order of about 7 solar masses and less die much more gradually and far less exotically than
how graceful
those that.
This sounds.
Yes.
It's so beautiful. We're gonna leave with just a whimper, not a bang.
It will be whimpery. Yes.
That's good. Good. I'm a big fan of all things ending with a whimper. Empires, and it turns out stars. So, here's a big question that was addressed in the video, but not. It was brought up. It was not addressed. So I'd like to hear either of you on this. Is if a supernova goes off close to Earth, will it destroy the Earth? Like, how powerful is it? I guess either one of you. I don't care. I don't care. No, I care. But either one wants that one.
It's been a while since I read up on this. Basically, the other interesting thing about astronomy is how far things are apart. And even the next nearest star is actually quite a ways away. But I do remember reading, and maybe Schuyler knows more about this than I do, that if a relatively nearby star exploded, it could, in principle, do some damage to us. Mostly the very highest energy gamma ray radiation from an explosion, in principle, could even sort of strip some of the atmosphere off the Earth, which would not be a good thing for most of us. So in principle, yes. In practice, it would have to be very nearby for this to happen. And none of our nearby stars that we know about are in the mode where they're going to do this anytime soon. So we don't really have anything to worry about. And so it's one of those questions that, yes, in principle, it could do some damage. No, you don't have to worry about it. Okay.
Okay.
Yeah. So I can add just a little bit to that. I mean, again, Betelgeuse is the closest red supergiant to us, and it's 500 light years away. And you would need a star to be within about 300 light years away for it to have that sort of impact. I mean, there was a supernova within about 25 to 50 light years away. It would probably lead to mass extinction. And it's not just the radiation, the light radiation from the supernova. It's all the particles that are created in that explosion as well, cosmic ray particles. They would probably have even more of an effect on the Earth than the actual radiation in the form of light. But it's just not likely because there just are no suspects that are that close.
Okay, so when you say particles, are you the word I'm thinking large particles? Are you talking about sort of gaseous particles or smaller
It's
particles?
subatomic,
Okay, yes.
subatomic
So
particles. Yeah, things
I
like
see.
electrons and protons and muons and all these ons.
Okay,
Yeah,
I get
of
it.
which atoms are made. Right.
That that is amazing. So I have so I have so of course I have a very basic question, which is, do you have a favorite supernova or supernova remnant?
I'll,
Uh,
Bill, why don't you
Go
take
for it.
the remnant one?
Well, why don't we start with the supernova? So go ahead with the
Oh,
supernova.
okay, all right.
Okay.
Well,
Yeah.
okay. In all honesty, all supernovae are my favorite, but I'll single out one in particular because it's the most special one to date, and that's supernova 1987A, which occurred in the Large Magellanic Cloud, which is only about 150,000 light years. Is that right? Did I do the conversion correctly? So that's
Yeah.
the closest visible supernova in over 300 years. And so not only were we able to see the star that exploded in amazing detail in retrospect, but we also got particles from it called neutrinos, which which are created in theoretically in the supernova explosion, and indeed they were observed from that particular event. Not many of them, only about 25 of them, over about a 13-second duration. But that was confirmation that we had a core collapse, as it's called, event that took place. And we're actually now seeing the formation of the supernova remnant in real time.
Oh, well, that's cool. That is a very cool one. I like the fact that I've got to learn how to pronounce the word Betelgeuse. Anyway, Dr. Blair, what's your favorite
So
remnant?
there, as Schuyler said, all the supernovae are his favorite. Each remnant has its own character, but I'll give you my favorite young one is known as Cassiopeia A. It was the explosion of about a 20 solar mass star, plus or minus a little bit, and it happened in the late 1600s. Interestingly enough, the supernova was not observed, even though it should have been. So that's kind of a mystery. But we can see the guts of that star that exploded in very great detail. And it's become one of the standards across all wavelengths to look at and try to understand. And it does have a compact pulsar or neutron star left behind as well from a massive star explosion. My favorite older one is called the Cygnus Looper, also known as the Veil Nebula. Uh, Very familiar object to amateur astronomers. The entire object is about 7 full moons across, about 3.5 degrees across. So if it was bright enough that you could see it in the sky, it would be this big loop of glowing gas on the sky, but it's too faint for naked eye, but easily photographed. This is one that's more like probably 10 or 15,000 years after the explosion. It's expanded out to very large size, and it is sweeping up interstellar gas into a big shell that is lit up now that we can see in X-rays and in optical and infrared radio wavelengths. And that's an example of an older one that is in the process of blending back into the interstellar medium. And again, that material will go into a future generation of stars and planets.
Wow. Oh, we have a question actually from the live feed, and feel free to like the Facebook page Universe Unplugged so that you can be alerted as to when the next one is, and go to universeunplugged.org to watch all the videos and get a lot of bonus material. The question is, Dr. Blair, you mentioned that there's a neutron star that's left. Why are they called pulsars?
So a pulsar is a neutron star that has a very strong magnetic field and spins very rapidly, so that when it's spinning around, as the poles of the neutron star sweep past us, we see a pulse of radio emission. and that happens every time it spins around. So, for instance, the Crab Nebula pulsar is spinning around 30 times a second, so we actually see 30 pulses of radio emission per second from that pulsar. Interestingly enough, the neutron star may be a pulsar in the Cassiopeia A remnant, but it's not pointed in our direction, and it doesn't show signs of actually being really active like the one in the Crab Nebula. So we think it's just a regular neutron star. That is to say, one, even if it's spinning, it doesn't have a strong magnetic field, and we're not seeing the radio pulses from that one. So a neutron star and a pulsar, they're both neutron stars, but one of them has a strong magnetic field and the other one does not.
Okay. Thank you, Todd Mason. I'm pretty sure that was from Mr. Mason. Now, we just got another one, which is, will the heavier elements form the center of a lower mass star ever be returned to space? How about you, Dr. Van Dyke?
Yeah, sure. I mean, so you were asking me, Jackie, about what happens
Yes.
to our sun. So the sun in its wimpy death will still lose all of its outer layers to the interstellar medium. All that will be left behind is the central core, which will have become this exotic white dwarf star. So all of those outer layers that contain elements that were inherited from the interstellar medium when the sun formed, as well as elements that it churned up as part of its lifetime, as part of its energy generation. Those will all be diffused into the interstellar medium as the outer layers are shed. They form something that's called a planetary nebula. So they're planetary nebulas are things like the Ring Nebula, which is a famous object. And so those last for thousands of years, and then they diffuse, much like supernova remnants, into the overall medium of space.
That makes sense. That makes so much sense. Okay, well, my brain is full, gentlemen. So I would like to thank you for joining us, and I want to thank everyone who's watching the video. And to learn more about the science of the Universe Unplugged video, Think Tank When Stars Go Boom, you can see that and all of our other Universe Unplugged videos at universeunplugged.org, or just click on the link in the comments. You can subscribe to the YouTube, and you'll be the first to know when the next video comes out. And you can follow us on Facebook to catch our next live chat. Thank you, gentlemen, doctors. That was fascinating. And until next time, I'm Jackie Cation, and this has been Universe Unplugged Live Chat. Take care.